Unit Operation Classroom. This is the website, and today we are discussing conditions for applicability of Bernoulli's equation. We all know and use Bernoulli's equation, but in this problem, we'll be discussing what are the conditions, inherent assumptions involved in deriving the Bernoulli's equation. So there are different conditions are given here, but before that, let's understand how the Bernoulli's equations have been derived. So first, so this is derivation and assumptions of Bernoulli's equation. The Navier-Stokes equation for an incompressible fluid, that means basically density is constant. So this is my first assumption. I'm not going to all the terms of the Navier-Stokes equation, but for an incompressible fluid, the Navier-Stokes equations can be like this, where this is the constant density, this is the substantial derivative of velocity vector with respect to time, and this accounts for the acceleration of fluid particle moving with flow. This, of course, is the negative of the grad P because the flow flows in the opposite direction. So that's the force due to pressure gradient. This, of course, is called the viscous term, and this particular term, of course, is a Laplacian of velocity, and this accounts for the viscous diffusion of momentum. This term right here. And this one right here is, of course, a gravitational force. And you can understand inherently or intuitively, this is nothing but the Newton's second law of motion. Why? Because once we understand what is substantial derivative, then it will become very clear. For an inviscid flow, the viscosity is zero. That means fluid, inviscid fluid, there is no viscosity. So if we make that assumption that there is no viscous diffusion of momentum, then that the viscous term can be neglected. So we'll neglect this term right here. So in that case, this equation reduces to this. So how this equation reduces to this? Two assumptions. First, of course, we have made the assumption that density is constant, and next we are assuming the viscosity is zero. So if we do that, then this term is here, this term is here, and this term is right here. Okay. This is called Euler's equation. So Euler's equation is derived from Navier-Stokes equation with two basic assumptions: that density is constant and there is the viscosity is zero. Okay, now we'll be focusing on this Euler's equation. What is a substantial derivative? Substantial derivative, of course, is a summation of the local acceleration term right here. The sub v is, of course, a vector, and v dot del v right here, which is, of course, a convective acceleration term. If we assume steady state, steady flow, then, of course, this local acceleration terms become zero. So this is, again, my third assumption. So I already made previous two assumptions, and this is my third assumption. If we do that, then, of course, this becomes equal to, so this is zero. So we substitute this one right here. So this becomes rho v dot del v right here is equal to this thing on the right hand side. Okay. Of course, v is the velocity vector. This is in the Cartesian coordinate, and v dot del can, of course, be written in this one. This is again the Cartesian coordinate system. So if we just write this equation, along a streamline, then we can, along a streamline, let's say there's a streamline, okay, then we can, a streamline S, let's say, so this would be rho, and this, of course, is V, this is equal to dV over ds, and that would be equal to the V, and this, of course, is dV over ds, and this, of course, is equal to negative of dP over ds, and this, of course, is equal to rho g dz over ds, right? Increment along the S streamline. Next is just some algebraic manipulation here. We divide both sides by rho, and this would be equal to, and we take this one on this side, so 1 by rho dP by ds plus V. So this one goes out as we divide. So this is equal to V dV over ds, which is right here, plus, of course, G dz over ds right here. That is equal to 0. And we integrate it along the streamline. So this is the integration streamline. So this becomes P over rho plus V square over 2 plus Gz is equal to constant. So this is basically called the Bernoulli's equation. So in the Bernoulli's equation, what are the assumptions? First, incompressible flow. Remember the very first one we did here. So that density is constant. It's an incompressible fluid. Okay. Next, of course, is the inviscid flow. We just discussed that. So this is my inviscid flow here. That's my second assumption. And the third assumption is a steady flow, which we did right here. So this is my steady flow, where the local acceleration term is 0, and flow along, of course, we have done the integration of the streamline. Okay. So this is basically, these are the assumptions involved Bernoulli's equation. So it basically says that the total mechanical energy per unit weight is conserved. So what along the streamline, if you take point 1 and 2, the total mechanical energy here must be equal to total mechanical energy here. So let's go into the problem now. So what are the assumptions? Incompressible flow, we have seen that is correct. Inviscid flow, we have seen that is correct. Unsteady flow, that is not correct because it is for steady flow. That is steady flow, we have made all the assumptions. So this assumption is not correct. And flow along a streamline. So A, B, and D are the true answers, true options. Okay. Once that, let's go into a little bit more on this Bernoulli's equation. We'll discuss, this is the additional notes beyond this, what is required for this problem. First of all, ideal form of Bernoulli's equation cannot be used in real life. Why? Because we're assuming viscosity is 0. But any real life fluid, of course, will have some amount of viscosity. Here it assumes in Bernoulli's there is no energy loss, but that is not possible. It also says total mechanical energy per unit mass or weight, depending upon whether we are talking in terms of head or energy terms. Fluid remains constant between 2 points along a streamline. So we can say along a streamline, if they're point 1 and 2, energy at point 1 must be equal to energy at point 2. So this is what it is. Okay. But as you can see, there is no viscous effect or viscous loss term included in this one. So in the extended form of Bernoulli's equation, which we as engineers use because we cannot use that ideal Bernoulli's equation, we have to make some modifications. So this is the extended form, and we'll look into it with momentum and the kinetic energy correction factors are also included in this extended term. So we can write this one as energy in plus energy added must be equal to energy out plus energy losses. Let's see what is meant by that. So you should have these terms, P1 over rho g. This is called the pressure head, and its unit is in, of course, length, meter. Okay, and this is, of course, the energy due to pressure. Alpha is called the kinetic energy correction factor. The value of alpha is equal to 2 for laminar flow, and the value of alpha for turbulent flow somewhere between 1.03 to 1.10, but normally we take this as equal to 1 for turbulent flow. Okay. And this, of course, V1 square over 2g. This is called the velocity head. Again, its unit is meter. This is, of course, the kinetic energy term. Z1 is, of course, the elevation head. Again, its unit is. So all these terms have the unit of meter. That's why they are called head. This is the potential energy term. And HP, this is the pump head. That means the head or the energy added to the fluid by the pump. And these are the same at the point 2. And HL stands for the head loss, the energy loss due to friction, fittings, valves, etc. Okay. Let's go slightly deeper into it. In the extended form of Bernoulli's equation, the head loss, HL, is due to friction. That means because of the viscosity. There can be two types of losses. One is a major loss, which is the pipe friction, and we all know this is given by this particular right here, HF. This HL is because of HF, major loss, and HM is the minor loss. This is given by this equation. We use this quite a lot. This, of course, is the friction factor. There are two types, of course, we know. There's a Fanning's friction factor and Darcy's friction factor. And these are given in terms of the Reynolds number. We know how this is. Low Reynolds number, of course, means the viscosity dominates, and high Reynolds number, of course, means the inertia dominates, because from this definition right here, And the values of F, of course, we all get from the Moody's charge or Colbrick equation or the empirical K values, which for the minor losses. Minor losses is for fittings, losses due to fitting, loss of head due to fittings or energy per se, fittings, valves, bends, expansion, contraction, etc. And for each type of fitting, valve, bends, we know there are certain values of K which we use. Important thing to see is that these losses are proportional to V squared. Therefore, you must be very careful about the velocity of what you're going to use because the loss is going to be proportional to the square of the velocity. And the pump head, of course, is given by this one here. Just note that almost 70 to 90% of the pump energy is used to compensate for the friction losses. We have solved quite a lot of problems on boundaries equation, and we'll be solving actual real life problems. But these are just additional points and the notes I thought I'd discuss with you. So again, going back, options A, B, and D are true.